All right, folks, so here is a video on week 12 Monday, number 3 and 11 from Reese's problems and number 3 from Chen's problem. So here is, let's start with number 11, okay? So number 11, here's the problem. We're trying to find out where it's decreasing, where it's concave down, and calculator is allowed. Okay, so I'm gonna increase this right here, or zoom in a little bit. Let's see if I can zoom in a little bit more here. Okay, so we're trying to find out where it's decreasing. Okay, decreasing means a negative slope. Okay, and we're given the graph of, okay, we're given the graph of slopes. Okay, so where the slopes are negative is where f is decreasing, and the slopes are negative here in between this x value and that x value. Okay, they just separate into two windows. Okay, so basically in between 4.29 and 8 and 7.48, okay, is where slopes is negative and therefore where f is decreasing. Okay, so so there you have it. Okay, what was I gonna say? Okay, and here for B, okay, let's look at B. Where is the interval concave down? Okay, where is it concave down? Concave down, okay, means the slopes are decreasing. Okay, so if you take a look right over here, if you take a look at this slide over here, whoops, where did I put it? Google Drive. No, I think it was in Unit 5. Key concepts here. Okay, if you look right here, okay, so this graph right here is concave down at the pink, and this is where slopes decrease. Okay, all right, so it's concave down at slopes decreasing. Okay, so so it's concave down at slopes decreasing. Now, this is right here the graph of slopes, and slopes are decreasing here all the way to here. Okay, all the way to the vertex basically. So let me go ahead and pull up that. Okay, so B, so as you can see right here, let me copy and paste that. B is decreasing, okay, it's concave down over until this x value 5.89. So it's concave down here because that's where this graph of slopes are decreasing. Again, let me sum that up. Slopes are decreasing. This is graph of f of x, and you can clearly see that it's concave down where the slopes are decreasing. This is the graph of slopes, and we can see it's decreasing where at this blue highlight up until this vertex, which is 5.89. Okay, so it is concave down from this x value right here, okay, all the way to this x value right there. Okay. Now, why is this? Now, I'm curious, why is this x value not 0? Right here, it should be 0, but okay. Yeah, because this is the graph of f of x, so the farthest left it goes is 0.41. Okay. Yeah. So basically, if you can go on Desmos and even zoom in on it, but they just basically scrolled all the way to, or found the maximum, did second calc to find the maximum. Okay, second trace to access calc, and then did maximum. Now, has a local maximum where f prime changes from positive to negative. That's obviously here, because here it's positive, here it's negative, and at that x value, do second trace and then go to zeros, which is your x-intercepts, and it's 4.2. Okay, and that answer C right there, because C is asking for where it has a local maximum. Local maximum is where the slopes go from positive to negative. Okay, if this is the graph of f, if this is the graph of f, is where the slopes go from positive to negative. That would be a local maximum. And here you can clearly see it goes from positive to negative here to here. Okay, so we find that x-intercept value, and that is where your that x-intercept value is where your maximum is going to be. Okay, let's look at number 3 from Reese's here. Okay, find the equation of secant line. Okay, so we have this graph over here. Okay, and basically, let's say the graph looks like this. Okay, or let me draw a better hypothetical graph. Okay, and you basically want the equation of secant line is basically y sub 2 minus y sub 1 over x sub 2 minus x sub 1 right here. So we have the x values here, okay, 2 and 5. So we plug in 2 into this, okay, and then we get the y value. Okay, you plug in 5 into this and you get the y value, and then and that's what they did here. Okay, that's what they did here and here. They plugged in 2 and 5 into this original equation right here, okay, right here, and they got these fractions, and then they just basically use y sub 2 minus y sub 1 and x sub 2 minus x sub 1 to get negative 1/4, okay, and then they basically picked any point in this case, again, here's your slope point. This is basically point slope form, so that's your slope, that 1/4. Let me get some highlights out the way here. Okay, so this is your slope, and they used the 0.2 comma negative 4/3, and they got that right there. Okay, 2b, again, going back to that graph earlier. Okay, we are that really crappy graph I drew, by the way. We're basically trying to find x values where it also has a slope of negative 1/4. Okay, so we're trying to find the x values where the slope is also negative 1/4. So basically, we're going to take the derivative of this, okay, to find the general equation for the derivative, and set that equal to negative 1/4 to find the x values where the slope is also negative 1/4. So here we take the derivative at b. Okay, at b we took the derivative and we got to this. So the derivative of this becomes this, okay? And we basically set this equal to negative 1/4 and did algebra cross multiplying. And they did all this stuff right here, and they got c equals to 3 and negative 1. Negative 1 is crossed out because that's not in the interval of 2 comma 5. Okay, so at c equals to 3, at c, which is x, equals to 3, you will also have a slope of negative 1/4. Okay, and find the equation of the tangent line through c is just basically using point slope form. So you can see, okay, we have the slope here, okay, of negative 1/4, which is right there. Okay, we have c, which is 3, which is the x value, and plug in c into this equation to get 3, and you'll get 3/2. Okay, and you get 3/2, and that's your y coordinate. So this is the x coordinate. Plug this into the original function to get the y coordinate, and you get 3/2. okay? Again, I usually like to write this on the other side and write y plus 3/2, but whatever, okay? So that's 3 from Reese's problems. Let's talk about 3 from Chen's problems, okay? So here, for Chen's problems, I gave you y double prime because I just didn't want you wasting a whole lot of time, okay? So let's look here. Let's go copy paste that. So you should definitely be able to get y. You should definitely be able to get y single prime, okay? Y prime, okay? So this is basically product rule plus the chain rule, okay? So here is keep first derivative of second, okay? Keep first derivative of second. This is chain rule right here. And remember, you can think of this as x to the power of, you can think of this right here as x to the power of -2, okay? Like that, all right? X to the power of -2. And when you take the derivative of that, you'll get -2 x to the power of -3, okay? Like that, all right? And that's how, so when you do derivative of when you do a derivative of this, derivative of outside leave inside gives you this right here. So this becomes that. And then derivative of inside, okay, of this right here, okay, let me, derivative of inside right here is this, which got carried over here. And then the second part of the product rule was keep second, or excuse me, derivative of first, keep second, which is here. So derivative of first became here, and keep second became here. Okay, so all I'm trying to say is product rule happened from here to here. All right, plus the chain rule with this, okay, to that. All right, now, this is algebra. This is just a whole bunch of algebra here. Now what they did was GCF a 2 and this, a 2e to the power of 1 over x squared from both, okay? And they're left with this right here, okay? And then they just simplified, this right here, this pink, to become this pink. And how did they do that? Okay, you can rewrite x. Here, let me draw with my mouse. It's not going to be the prettiest, but it should get the job done. They rewrote this x into x squared over x. And then this whole thing, they just flipped it left and right. They just rearranged it. X squared minus 1 over x. Okay, and now this pink became that pink because you factor. Okay, you factor x squared minus 1 to x minus 1, x plus 1, you get this. Okay, so now we have some critical values over here. Okay, we got some critical values of 1, -1, and also 0. Okay, so they just basically did, I like to draw the number line. Okay, I like to draw the number line, and they just did it in a table format. Okay, so let me draw the number line here. Boom, boom, black, let's go number line. And they put, and I'll go -1, 0, 1. Okay, again, they just did table format. Okay, and when you, let's pick 2 here. When you plug in 2 into the slope formula, or the y prime, okay, 2 plus 1 is 3, 2 minus 1 is 1, so this is positive and positive when we plug in 2. 2 squared is 4, 1 over 4, e to the power 1 over 4 is positive, 2 times a positive number of that. This term is also going to be positive, and this is going to be positive, obviously, so this is going to be positive. Okay, over here, okay, let's say we pick something in between 0 and 1. Let's pick half, okay? 1/2, okay, let me erase some of these markings I made over here, okay? 0.5 plus 1 is positive, 0.5 minus 1 is negative. 0.5 squared, basically this will always be positive because e to the power of whatever, whether it's positive or negative, is always going to be positive. 2 times a positive number is positive, okay? And this is positive because 0.5 is positive. So you basically get positive times positive, which is negative, over positive, which is a big fat negative right here, okay? And let's repeat this process over here. Let's say we pick negative 0.5. Negative 0.5 plus 1 is positive. Okay, I'm picking something in this area. Negative 0.5 minus 1 is negative. We established that this is always going to be positive. This is negative because it's negative 0.5. This becomes negative on top. Okay, this stays negative on bottom, and this becomes a big fat positive. So this is positive over here. Okay, let's pick negative 2. Okay, let's pick negative 2. So negative 2 minus 1 is negative. Negative 2 minus 1 is negative. Okay, remember we established this is always going to be positive, and since negative 2 is negative, that's going to be negative. Positive times negative is positive, over negative on bottom becomes a big fat negative. Okay, so the slope is negative, which means the slope is negative, which means f of x is decreasing. The slope is positive here, which means f of x is increasing. This is decreasing, increasing. Okay, so that's why it says decreasing, because this says decreasing, increasing, decreasing, increasing. That's what we got over here. Okay, so at these intervals, okay, it's decreasing, increasing, decreasing, increasing. Okay, so that takes care of A and B. Concave up, I gave you y double prime. So concave up, let's look over here. Let me copy and paste this here. Boom. Okay, copy and paste and delete these highlights. Let's look over here. Okay, so some critical points, all right, some critical points over here for C. So here's your double derivative over here, and you really have no critical points because we already established that this is always going to be positive right here, okay? This right here is always going to be positive because of this squared. Any number squared, positive or negative, is going to be positive, and this is also always going to be positive because anything similarly squared or to the power of 4 is going to always be positive. So this whole thing is always going to be positive, okay? Because positive times positive on top is positive, divided by positive is positive, okay? So the only place where it's not defined, where you're going to have a possible inflection point, okay? Let me look here. The only place where you're going to have a possible inflection point is over here when x is 0, okay? When the denominator is 0, okay? So for your inflection point, so let's do a number line here, okay? Let's do a number line. Okay, so here we go. I'm going to put 0 in the middle. Let's pick something like 1 over here. Okay, it's not, well, we already established it's always going to be positive. Okay, because this we just like I showed over here, this whole thing is going to be positive. This is going to be positive, and this is going to be positive. Okay, so whether we pick 1 here, it's going to be positive, or we pick negative 1 here, it's still going to be positive. Okay, so it's always going to be concave up except for at 0, because 0 is going to be undefined, and therefore we have this. Okay, it's never going to be concave down because you never get negatives here. Okay, that's why D. Okay, so earlier C was concave up except at 0, and now concave down it is never, because it's never negative. Okay, inflection points. We're tempted to say 0 is an inflection point because it makes this undefined. okay? But it's actually, what was I going to say? Not an inflection point because we do not have a sign change, okay? We do not have a sign change. Jeremy, you can turn on the light over there, bro. Jeremy, you can turn on the light over there if you want because you're up in the dark. Jeez, man, feel bad. Okay. Sorry, I was talking to one of my students. Now, lastly, and local extreme values is where going back to here. Okay, press one of those buttons should work. There you go. Much better, yeah. So lastly, folks, local extreme values is going back to here. Okay, is where you have a sign change. Okay, is where you have a sign change going back to F single prime. Okay, I should have actually talked about E after B. Okay, so again, if you have a negative slope and then see this is a negative slope, that's a positive slope, you have a negative slope, then a positive slope, this is a local min. If you have a positive slope, then a negative slope, this is a local max, and this is a local min. So you have a min at you have a minimum at x equals to -1 because it goes from negative slopes to positive slopes. So at x equals to -1, you have a minimum. Similarly, because you go from positive slope to negative slope at x equals to 0, okay, you have a maximum. And by the same logic, because you're going from negative to positive at x equals to 1, you have a minimum. Okay, and that is what is showing local and absolute minimum over here at 1. So we have two minimums right here at 1 and -1, and they just basically plug that into your original equation to get the e's right here. Okay, let me see the original equation over here. Where is it? Where's the original equation? Yeah, so they plug in 1 and -1 to here, and they basically got E for both for this coordinate right here, E. Now I'm wondering how come this was not right here. How come this was not listed as a local maximum? Okay, because this should be listed as a local maximum over here. Let's see the graph on Desmos real quick. Okay, x squared, graphing calculator, x squared, x squared e to the power of 1 over x squared I see what happened. Because 0, when you do a quick look at the original function, 0 doesn't count, even though typically, like I said earlier, this would be a local maximum, because when you plug in 0, 0 squared is 0, 1 over 0 is undefined. So it's actually undefined at 0, so it cannot be a local min or max. Okay, folks, that's all. That wraps it up. Thank you for tuning in.